Hi, I'm going to explain to you how to do these questions then. So question 1 shows a search coil positioned on an axis of an electromagnet with the plane of the search coil perpendicular to the axis. A magnetic field is produced by a constant current in the electromagnet, and assume the magnetic flux density inside the search coil is uniform. So if you were to put the search coil inside here, you wouldn't get any electricity generated because it's constant. As we move away from here, the field lines will spread out because they're coming out like this. So the magnetic flux density will go down, which is shown in this graph here. And it says the search coil is placed at x equals 0.07 meters. And it show the magnetic flux linkage is 5 times 10 to the minus 4 Webers. So we know x, we know n is 200 because it tells us here in the question. And we know the cross-sectional area is 3.5 times 10 to the minus 5. Magnetic flux linkage is NBA. What we don't know is B. So what we need to do is go to the graph, find 0.07. So it's 0.06, 0.07, draw a line up. You should use a ruler and a cross. And I got B as 0.068, although I think there's a range of answers you can have. Substitute into there and you get 4.76 times 10 to the minus 4, which is approximately 5, which is what you want. Okay? It says then the search coil is now moved at a constant speed along the x-axis, so x is increasing, so it's moving this way with the speed v. So we know that the magnetic flux density is going to go down. Explain what happens to the value of the EMF as the search coil moves. So there is a rate of change of flux linkage, okay? But it is reducing because your the field lines are spreading out. Oh, hang on, my computer's just switched off. Yeah, so that gives you, but it is decreasing. So the first mark is for saying that the flux linkage is decreasing. And then that means that the EMF is proportional to the rate of change of flux linkage. So therefore it is reduced as well. Okay. Right, the search coil passes through a point where x equals 0.1. Deduce whether EMF can exceed 5 millivolts or greater for 0.1 meters. So we're going to use EMF equals NBA over T. We know N, we know A, okay? We then need to figure out what we're using this velocity value. So we're going to say, well, T is distance divided by velocity, okay? Sub it in here. So EMF equals NBAX over V. Tidy it up a bit. I'm just going to put NAV there, and then we've got B over X here. And that is the gradient of the graph. So we know N, A and V, and then we need to find the gradient of the graph because it's the rate of change of flux linkage at 0.1. So you draw a tangent to the line at 0.1 with a ruler, which I don't seem to have. 1 second. Here. Work out the gradient. So I worked out my gradient as minus 0.74. okay, and then sub it into here. So you've got 200 times 3.5 times 10 to the minus 5 times V, which was 0.8 times minus 0.74. And it comes out with an answer of about 4 millivolts. So if you're getting around 4, obviously your gradient might be slightly different. So no, it can't exceed 5. Very, very hard question there for 4 marks. Okay, next. Question 2. The diagram shows the variation of time in the magnetic field flux density B of a field coil. The graph shows the variation of induced EMF. Which one's correct? The gradient of this will tell you the EMF because it's the rate of change of flux. Okay, now the rate of change of flux is not changing, so you get a constant EMF for both of these because their gradients are constant. So it's either C or D because you get a constant EMF. The steeper the line, the greater the rate of change of flux linkage, and the steepest line is this one, so it will have the biggest EMF. So it's C. Yeah, because the gradient is bigger, so you get a bigger EMF. So the answer is C. Okay, question 3. The diagram shows a square coil with a plane parallel to a uniform magnetic field. The coil always remains within the magnetic field. These are the 4 possible positions. How many of them will induce an EMF? So if you want to induce an EMF, you need to change the amount of flux. So if we move it to the left this way, the amount of flux in the coil doesn't change. So that one doesn't. If you move it towards Y, the rate of flux change doesn't change, like you're still going through the same amount of flux lines at the same rate. So that one isn't. If you rotate it about XY, that's like spinning it around XY, that will change it because you go from a maximum to a minimum to a maximum to a minimum. So that one will. And if you rotate it about Z, which that is at the centre and perpendicular to the plane of the coil, that won't change it because you get the same amount of flux all the time because it's rotating with the field lines. So it's not that one. So it's A, just one. Okay. Right, number 4. You've got a square coil of wire rotating at a constant angular speed, so it's rotating this way. Figure 1 shows the coil at one instant when the normal to the plane is 30 degrees to the magnetic field. The area of the coil is 5 times 10 to the minus 4. And the flux density of the uniform magnetic field is 2.5 times 10 to the minus 2 Tesla. The maximum flux linkage of the coil, N phi, is 1.5 times 10 to the minus 3 Webers. Calculate the number of turns in the coil. So N phi equals NBA. Okay, so this N phi is 1.5 times 10 to the minus 3. N we want to find. B is 2.5 times 10 to the minus 2. And A is 5 times 10 to the minus 4. So then a straight rearrangement to find N, and it is 120. Okay. Then what happens is calculate the flux linkage of the coil at the instant shown in figure 1. You couldn't do this before, I don't think, but if you look at the, I think you should be able to do it now you've done Chris. If you look at the equation in the booklet, you can actually put cos theta into the term. Okay, so if you put the cos theta in, so we know the flux linkage is 1.5 times 10 to the minus 3, so BAN is equal to 1.5 times 10 to the minus 3, and then you can just put cos 30 in, and it gives you 1.3 times 10 to the minus 3. That number is smaller than the maximum, so we know it's right, because the maximum is when it was upright. Okay. The coil forms part of an electric generator. Calculate the peak volume of the EMF generated. I can't remember what the answer to this is, but it's on the mark scheme, but you should be able to do that with Chris, but I've not done it, so I'll just leave that. And then number 4, sketch in figure 3 the variation of the flux linkage. So if we do our little sine x cos x minus sine x minus cos x, we want because the gradient of this tells us this, we want to integrate this, okay? So our EMF is a positive sign, okay? Integration means we go up. So the integral of a sine x graph is a minus cos x graph, but flux EMF is proportional to the negative of the rate of change of flux linkage. So rather than a minus cos x, we want to plot a cos x. So it will look like this. It's easier if you draw your dots as you go along. And then you've got a nice positive cos graph here. Your exam board actually doesn't care if you don't know about the minus thing. So if you plotted a negative cos graph, that would also be fine. Okay. Next question, question 5, last question. I think you've done this one with Chris as well today. So a rectangular coil is rotating anti-clockwise, so it's going this way. That got me really confused. At the instant shown in figure 1, the angle between the normal plane of the coil and the direction of the magnetic field is 30 degrees. State the minimum angle in degrees which the coil must rotate from its position in figure 1 for the EMF to reach its maximum value. The maximum value will be when it is the rate of change of flux linkage is greatest, which is actually at this point here. So this, by similar angles, that angle there is 30 degrees, so it needs to go through 60 degrees to then get to there. Okay. And it says calculate the minimum angle in radians which the coil must rotate to get for the maximum flux linkage. The maximum flux linkage is when it then gets to here, so it's got to rotate here and then get to the top again. Okay, so you've got 60 plus 90, which is 150 degrees, but it wants it in radians. So to convert radians, you do the degrees times 2 pi over 360, which gives you an answer of 2.6 radians. Now, figure 2 shows how, starting in different position, the flux linkage coil varies with time. What physical quantity is represented by the gradient of the diagram? So this is the gradient of the flux linkage, will give you EMF, okay? But it's the negative. So it's the negative of the induced EMF. But your exam board don't care about the negative, but you should be, it's correct to put that. It then says calculate the number of revolutions made per minute by the coil. So if we look at the time period is 40 milliseconds. Okay. So if we did per minute, if we did 60 divided by 60 minutes in, sorry, 60 seconds in a minute, isn't there? Divided by 40 times 10 to the minus 3, that 40 milliseconds, it'll tell us how many revolutions it makes per minute, which is 1,500. And then it wants us to plot the graph of the induced, it wanted us to calculate the peak EMF, which you should be able to do now from Chris's lesson, but I've not done it, so I'll just leave it. You can check the mark scheme if you've got it right. And then sketch a graph on the axis of figure 3 to show how induced EMF varies with time. So if we write our sine, cos, minus sine, minus cos, we're differentiating this. The gradient of this tells us this. So we're going down. And here we have a minus cos graph. So the gradient of a minus cos graph gives us a sine graph, but we want the negative of it, so it's a minus sine graph. So it will go down first. Plot your points before, because it makes it easier. Once you've got the pattern, it's easy to just do it. If you do a plus sign graph, your exam board doesn't care and it will give you the right answer. Oh, I've done that wrong. That should go to there. That should go to there, not in here. No students in here. And then the coil has 5. Go into my office next to S4. Right, so 550 turns. N has 550 turns and a cross-sectional area of 4 times 10 to the minus 3 meters squared. Calculate the flux density of the uniform magnetic field. Flux density is N phi equals BAN. That's what we're going to use. We want to find B. So B equals N phi over AN. What we use then is the graph to find N phi, which is the maximum flux linkage from the graph. So you just read the top of this graph here. Do you? Hang on, where did I get that from? 0.55. Oh, hang on, I'm not sure where I've got that from. I can't pause this video, 1 second. Oh, I think you get it from this one. Yeah, you do, from here. This is 0.55 there. So just check the units. Yeah, it's just 0.55. So I've lost the question now. Here we go. So 0.55, and then you divide it by the area, which is 4 times 10 to the minus 3 times 550. So that gives us a value of 0.25 Tesla. Sorry about the interruption during that last bit of the question. Someone just walked into the office. Hope that's all okay. If you need anything explained in more detail, please let me know. I can't stop. I can't stop you. Yeah, I have, but I can't stop it, so just be aware, whatever you say. Oh no, it doesn't matter, it won't pick it up. Oh yeah, there you go. If I close